All right. Intermediate value theorem is a brand new concept. It was not touched on in the pre-calc book at all. Very obvious, I think you'll find. If f is continuous along the interval from a to b, so essentially if some function, and we've got 25 of us in here, we could draw 25 different graphs as to how to make it so a to b is continuous. So I don't know, I'll do mine like that. You can do whatever you want. You could go down first from a and then up to b. Doesn't matter, as long as it's a continuous function on the closed interval from a to b. And they say if k is any number, any value between f of a and f of b, so k is anywhere between here, I'll just throw it there. Again, you could throw k wherever you wanted. But if k is between f of a and f of b, then there has to exist at least one number c between a and b. So there has to be at least one location, maybe more, depending on your graph, between a and b such that f of c will equal k. So here's essentially k is there. So based on my graph, my c value is there. And there has to exist at least one. Does anybody have 2 from their graph? Like if 2 c values? Because I could change the location of my k to being like down here. So I still have my same continuous function. I'm picking a different k between f of a and f of b. So for at least one number c, well, mine now has 3 of them. Here's a first c value, here's a second c value, and here's a third c value. But it has to happen at least once, because if you're continuous from a to b, you have to cross every value between f of a and f of b at some point to get there. So, pretty straightforward. The only time you wouldn't have to cross all of the values between f of a and f of b would be if there was some weird jump, right? But there can't be, and which is why they have this stipulation that it has to be continuous. For example, if I had, and you don't need to necessarily draw this, but if I had f of a here and f of b here, but I did some sort of piecewise function, and then k happened to be there, now there wouldn't exist a c value between a and b that hit that. So that's obviously not in the cards because they give us that stipulation about continuity. So maybe if you have your review packet with you printed out, I might grab it just to show you what a multiple choice would look like when we get through, if we have time. So these are kind of the instructions that your homework will give you. Explain why this function must have a 0 in the given interval. So why does this function have to have a 0, meaning a root, in the interval from 0 to 1? So visually, from 0 to 1, this is saying that this function has to have a root between 0 and 1. And how can we prove that? Any ideas? Alyssa? Perfect. So we'll show you kind of what she's saying when we do it out. F of 0, when you plug it in, gives you -2. So that's a negative number. F of 1, when you plug it in, 1 plus 3 is 4, 4 minus 2 is 2. So f of 0 is -2. And f of 1 is +2. And the third stipulation is what? Or the main stipulation that we know about this function. Right, this function is continuous along that interval, right? So we're not going to experience any jumps or anything. So there must exist, if it's going from negative here, and it's got to be positive by the time we get over here, and it's continuous in between, then we kind of have to cross that line, don't we? Well, it's more of an explanation. Explain. So you show this, you show that you calculated this, you'd say two things. Since f of x is continuous from 0 to 1, that's this one stipulation that you have to make sure you're checking for. And f of 0 is negative, while f of 1 is positive. And I'm going to try to write as few words as possible, but what I'm going to try to say here in as few words as possible, there has to be some number between 0 and 1 where f of that number will equal 0, because it goes from negative to positive. So if it's on this continuum and it goes from negative to positive, it's got to cross 0. So we just want to find an efficient way of writing that to save time and energy. So since f of continuous and f of 0 is negative while f of 1 is positive, there must exist some x value between 0 and 1 such that f of x equals 0. It's almost so obvious, it's like, why are we doing this, right? It's not, it's almost like doing the topic makes it more confusing than it needs to be. But there are things, as we move further through calculus, that you'll say, oh, the intermediate value theorem, and we'll use it to kind of justify things later on. So this one wants us to prove that we have a 0 in the interval from 1 to 3. So f of 1 is going to be negative 4 plus the tangent of pi over 8. We don't know the tangent of pi over 8, correct? What do you know about it? Liam. It's positive. What's the tangent of pi over 4? 1. And this is smaller than pi over 4. So the tangent of 0 is 0, and the tangent of 90 is undefined. At pi, and it's increasing, right, as we get there? The tangent of pi over 4 is 1. So pi over 8 is going to be a small positive number, yes? So when you take negative 4 and you add back a small number, most importantly, we're still negative. Without a calculator, that's the best we can do, is just knowing for sure that we're in the negatives. And then f of 3 is negative 4 thirds plus the tangent of 3 pi over 8. So this is like negative 1.3 repeating. Plus, this is 2 pi over 8. So 3 pi over 8 is going to be here. This one, I wonder if this actually does have the other calculator, because this one would be tougher to, I mean, we can all pretty much predict it's going to be positive, right? Just based on the intermediate value theorem, wouldn't be able to apply if it wasn't. But I'm going to guess that this has a little calculator next to it. Where did I take this little guy from? I think you need a calculator, then you do. Because if I can't do it without a calculator, I would never expect you to. So I'll just type that in just so we can have an exact number. Negative 4/3 plus the tangent of 3 pi over 8 is barely positive. So that would be, tough to actually prove. Tan of 3 pi over 8 equals, I'm just going to say positive. So you just have to show that one's negative, one's positive, because that's surrounding the 0 that we want to make sure we have a 0. And we want to show that this is continuous, okay? This would be discontinuous where? 0, but we don't have to worry about that because that's not in the interval. And this is going to be discontinuous, obviously, also at 0. Oh, no, not at 0, this part. When x is what? When's the first moment that this will be undefined? When x is 4, which we also don't have to worry about. So we just make the statement. You don't really have to justify it, but you do need to say, since f of x, it's going to be very similar to this one, is continuous from 1 to 3, and f of 1 is negative, while f of 3 is positive, there must exist some x between 1 and 3 such that f of x equals 0. On a test, it will just be one time. On your homework, just make sure you can write a sentence. Struggle through it, Josh. Just do it. What's that? Well, I don't think there's too many that will say explain on your homework. Pencil's dying. All right. On the next exercise is a calculator type of question. And on that first one, there's a typo. It should be a minus 4. So change this to minus 4. So on your calculator, it wants you to approximate your zeros on the interval from 0 to 1. Zoom in just to 2 decimal places at first. So on this first one, and you can do it or you can just watch me. Make sure you're in radians, tan of x plus 3x minus 4. And it wants us to show that there's a 0 between, on the interval from 0 to 1. So as far as my window is concerned, I can just go from 0 to 1. And then my y min and my y max, again, I can go from negative 1 to 1, and that should be enough to kind of show my root between 0 and 1. So it's way over here. So the first one, it wants you to zoom, and I'll zoom in, and I'm going to go over and zoom in there just one time, and then I'll just try to get over there and round it to the nearest, 2 decimal places. So 0.91. Well, then so following zoom in and round to 2 decimal places, theta equals 0.91. Then they do want you to use the root feature and do it more to the nearest fourth. So 0, second trace, option 2, which is 0, left bound, enter, right bound, enter, and to the nearest, or out 4 decimal places, so 0.9071. When the writers wrote this, I don't really know the purpose of having these like that. As far as the intermediate value theorem is concerned, this is continuous between 0 and 1. You don't have to worry about anything there. Right, because 1 would be 1 radian, which is like here. So 0 radians to 1 radian. So the tangent doesn't have an asymptote there. So it's continuous between 0 and 1. If you plugged in 0, you'd get negative 4. And if you plug in 1, you'd really need a calculator to show that that's positive, because we don't know what the tan of 1 radian is. But it would be 0, and you can see it on your graph. If I go back to this, 0 to 1, and negative 1 to 1, you can see that f of 0 is a negative number. It's coming from the negative side. It's coming from negative 4. And then f of 1 is a positive number. So somewhere in between, because it's continuous this whole stretch, it's got to cross a root. And the next one, same concept, just on your calculator, just a log function of 5 log x plus 1, and then minus 2. Window, it's fine. So f of 0 is clearly a negative number. F of 1 is clearly a positive number. It's continuous in between, and so obviously it crosses 0, and we could zoom in and do all that. Same idea. Okay? Any questions so far? All right, so if you flip to the back, verify that the intermediate value theorem applies. So that verification is really a 3-step process. The continuity, and then the f of 0 at the start of your interval, and f of 3 at the end of your interval. And then find the value of c that is guaranteed by the theorem. So, again, just verify, just state that f of x is continuous along the given interval. Which doesn't say we have to explain it, but we all know quadratics are continuous everywhere, so not really much to worry about there. And then f of 0 is going to be 8. F of 3 is going to be, what kind of number do you know without even plugging it in? A negative, right? This one's a little bit different than the other ones. The other one started negative and ended up positive, so we knew we had to cross 0. This one's clearly starting positive, so I would assume that when I plug in 3, I'm going to get a negative number. 9 minus 18 is negative 9, plus 8 is negative 1. Okay, so because it goes from positive to negative, it has to have crossed 0 somewhere. Now find the value of c that is going to make that happen. So set this equal to 0. Solve. It's a factorable one. So it's either at x equals 4 or x equals 2. Which one is it? So we just found the location that guarantees the 0. But we have 2 of them, and one of them is the one we're looking for, and one is not. Liam? Right. So we're looking for the x value that's in the interval, so that would be just the 2. Okay? So visually, we've got this quadratic that's got roots at 1, 2, 3, 4, and 2, and it opens up. Okay? But they want the intermediate value theorem. I didn't mean to put that there. There's no root at negative 2. It's at 4 and 2. The roots are at 1, 2, 3, 4. So 2 and 4, and it opens up. So that's what the parabola looks like. This has us narrowing in on the interval from 0, which is here, to 3, which is here. So that's why we got our f of 8. F of 0 was positive 8, positive number. F of 3 was a negative number. It's continuous in between, so of course it must pass. And we're taking this answer because that's the value between 0 and 3. On our second one, starting with continuity, where is this function discontinuous? Okay, so if I factor and simplify, nothing really cancels out. It is discontinuous with an asymptote at 1. We don't have to worry about that, though, right? 2.5 to 4 is essentially what this is. So from 2.5 to 4, if we're discontinuous at 1, we don't care. That's prior to this interval. So you would say that f of x is continuous along the interval. Then f of 5 halves. Oh dear. This probably going to be a calculator. So we're plugging in 2.5. So 2.5 squared plus 2.5 gives us our numerator. Divided by 2.5 minus 1 is going to be 1.5. So it says 5.83 repeating. And f of 4 times 5 is 20. 20 divided by 3. 6 2/3. 6.6 repeating. So this is a little bit different, because now they're not trying to get us to prove that we have a root where f of c equals 0. They're trying to find a c value where this equals 6. One of the endpoints of your interval is less than 6. The other endpoint of your interval is greater than 6, and it's continuous in between, so it's got to pass 6. Yes? As far as our graph is concerned, like kind of getting at our definition from the front side, 2.5 would be at 5.83. And then 4, when we plug it in, is going to be at 6.6. And we know it's continuous in between. So, of course, we have to cross 6 somewhere. So that verifies that the intermediate value theorem applies here. So this is the first time we've seen that it doesn't have to just be a 0. It's any y value. In this case, we're surrounding 6. We're below it, we're above it. So we have to cross 6, and it wants us then to find out exactly where. So find out exactly where that will equal 6. So x squared plus x over x minus 1. And we're going to find the x value that's between 2.5 and 4. So to solve this, we'd have to cross multiply. Got another quadratic on our hands. Subtract your 6x over, add 6 over. Factor, you get x minus 3, x minus 2. So it's at x equals 3 or x equals 2. And which one is it? Based on the interval we're limited to. X equals 3. Got to pick the number that's between 2.5 and 4. So right here at 3, it would cross at 6. I think the verifying, the intention of that is just to get you reinforcing the rule that it, you can't have jumps, obviously. What was your question? I think they're just reinforcing the theorem and understanding the 3 components, really. Yeah. And then the last one is more of an application for the volume of a sphere. So the volume of a sphere is based on the size of its radius. So I'm just going to give you the formula of that because I didn't remember it. Good. So it wants us to use this intermediate value theorem to show that for any spheres with a radii between 1 and 5, you're going to have one somewhere in there that's got a volume of 275. So essentially, number 1, first stipulation, this is continuous. So V of R is continuous from 1 to 5. And then V of 1, the volume when the radius is 1, I'll just do 4/3 pi times 1 cubed, 4/3 pi r cubed. That volume is 4.189, I'll do. Centimeters cubed. And when the radius is 5, 4/3 pi r cubed, your volume is 523.599. So obviously there's some radius in the middle, some v of r between 1 and 5 that will have a volume of 275, since one of those numbers is less than 275 and one is greater than 275. And then to figure out what radius that would be, what radius would it be that would yield a 275? We just would solve the equation. 275 equals 4/3 pi r cubed. So multiply both sides by 3/4 to start. And divide your pi over. And then what do we do to both sides to get rid of the cubed? Cubed root, or raise it to the 1/3 power, and it gives you a radius of 4.03. So V of 4.03 is the one that gives you a volume of 275. So some book work tonight, but it's a little bit limited on what it does for intermediate value theorem, so I also have a worksheet for you that I will hand out. In the meantime, do you have that packet? Oh, we have like 1 minute. All right. If you have it handy, I'll throw it up and let you read it while I pass out the things I need to pass out.